it's my pleasure to introduce our second speaker this afternoon, José Ferreira Alves. Well, José is virtually back home since he has obtained his PhD at IMPA a few years back. So he's a frequent guest and a great collaborator of the Brazilian mathematical community. So I imagine he needs not a further introduction. So just let me mention a very nice recent contribution for the mathematical literature that he has done, the book, Non-Uniform Hyperbolic Attractors. So it was published last year by Springer. It's a very nice book. I suggested it for everyone. And a bit of an ad. And José is a full professor at the Universidade de Porto in Portugal. And today he's going to talk for us about the entropy formula for systems with inducing schemes. Thanks, please.
Okay, thank you very much, Jacqueline, especially for these kind words about my book. I will make several references to the book. Also, I want to thank the organizers for this the invitation to speak in the Brazilian Colloquium of Mathematics. So I will talk about a recent work with David Mesquita, a PhD student of mine, which is the entropy formula for systems with inducing schemes. So I guess you all know what is entropy, and many of you know that what is also inducing schemes, and that many systems have inducing schemes, and inducing schemes can be used for many purposes, for proving some statistical properties of systems. And here I'll deduce one more property of system is I deduce the existence of an entropy formula. So I will start with the definition of entropy that you must all know, but especially for the notation, I think it's important. So we have some dynamical system preserving some measure, and we have a mode 0 partition. We can define the entropy of the partition, which is defined in this standard way. And then we can define the entropy of the system with respect to the partition. And is this infimum overall 1/n entropy of this. These are the dynamical refinements of the initial partition. And so, and in the end, we define the entropy of the system, measures dynamical system, as the supremum over all partitions of the space. Well, as you know, this is very interesting. It in some sense measures the complexity of the system, but only looking at these expressions, we see that it's, well, not for computing the entropy is not very practical. So we try to find formulas for this entropy. And there are some classical results. The first one by Ruel, actually is the second one, because there was a first result by Margulis in the same direction, but for some special class of measures, and Ruel generalized it for all measures or any invariant measure. And he gave an upper bound for the entropy as the integral. So the integral of the positive Lyapunov exponents is an upper bound for the entropy. Then Pezin proved that we, in fact, have an equality for measures which are absolutely continuous with respect to volume measure or Lebesgue measure. That's what I would call an SRB measure. And Le Drapier and Yang later actually characterized the measures satisfying the Pezin entropy formula. Actually, they satisfy the Pezin entropy formula if and only if they are absolutely continuous with respect to the volume measure. And just to mention a few, there are more results in this direction, but I would say the more classical results. There is some result several results by Katok, Strelsin, Le Drapier, in a book with Zetinsky as well. And there are several chapters of that book dedicated to prove the entropy formula for maps with singularities. And these are the maps that we are more concerned here in this talk, because there are not many results for this kind of map. So by singularities, I mean discontinuity points or points with where the system is not smooth, because all these results above They are for smooth dynamical systems, and some of them for diffeomorphisms. They also have generalizations for endomorphisms, but for maps with discontinuities or points where derivative does not exist or is infinity, just a few results. And one of the important ones, so the most important ones, I would say, are contained in this book by these 4 authors, and they are mostly motivated by billiards. But as I said, there are several chapters dedicated to this entropy formula. The assumptions are not very easy to check. Well, they are easy in the case of billiards, but in general, they are not easy to check. We need some assumptions on the measures, some to check some hypotheses. So it's not very practical. So my focus here will be on systems with singularities and using, well, a lot of new results that we have, in particular the inducing schemes for dynamical systems. So let me start by telling you what is the class of maps we are going to consider. So we consider maps defined on a Riemannian manifold, and we consider m, little m will be the Lebesgue measure or the volume measure on that manifold. We assume that the map is piecewise C1 plus holder. By this I mean that there are pairwise disjoint open regions in the space M, countable number of them, such that the union of their closures is the whole manifold, and the map restricted to any of these open regions is C1 plus holder. So this is the kind of maps that we are going to consider. We will refer to the set S, which is the complement of the union of these open regions. We'll call this set the singular set. So it's a set of points where in principle it can be non-continuous or non-smooth or even with infinite derivative. So this depends on the situation we are going to apply, but these are the possible types of singular sets. Okay, so this is the class of maps, and let me tell you what are the inducing schemes. So assume that we have a map as described before, and take some region in the space, which is actually disjoint from the singular set, and we assume that the region has a positive volume. And for that, we are going to consider a countable mode 0 partition that we'll call P of this region that we are going to select in the space, and a function which essentially assigns to each element in the partition a natural number, so a positive integer. Okay, so these are the inducing times. And we assume that from 1 to, it iterates from 1 to this natural number that we assign to each element of the partition. We assume that the iterates of each element in the partition is disjoint from the singular set. And we also assume that in the end, so in the last iterate, so the R of omega, we return to the same region. Okay, so we have the image of that domain is contained in initial big set, delta 0. So in this way, we can associate to these objects a new map, a map from delta 0 to delta 0, which is defined M almost everywhere, but it's no problem. So, and the map is defined in this way. So for each element in the partition, we consider the respective power of F. And so I will call this new map, I will call it capital F. And it is often, sometimes it's useful to use this notation, which indicates also this function, which is the recurrence time. So instead of F, I will call it F power to the power R, but of course the R depends on the domain we are considering. And this is called the induced map. And the function R is called the recurrence time associated to this induced map. And we say that the induced map has integrable recurrence times if this function R is integrable with respect to the volume measure on delta 0. Okay, so this is essentially notation and terminology. Okay, so these are the inducing schemes, but we need some more properties to deduce some properties, in particular for the initial dynamical system. And so we are going to add 3 more properties to these induced maps. So, and with these three more properties, I will qualify them as a Gibbs-Markov map. So this means that there are constants C, alpha, and beta in such a way that, well, the first property is a full branch property. So each domain, when it returns, it actually goes to the whole set where we are inducing, the delta zero, okay? All of this is bijectively mode zero always. We have expansion. And expansion here means, so we will consider, if it were in dimension one, I would simply say that derivative would be bigger than one, strictly bigger than one, but we are going to consider higher dimensional, well, we want to apply to higher dimensional systems. And so the way of saying that we have expansion is that the inverse of derivative, which is invertible on the image of each domain, and the inverse of the derivative is strictly bigger than this number, which is smaller than one. Actually, the number is strictly smaller than one. Okay, so full branches, expansion, and the third property which is bounded distortion. So the determinant is essentially, this is saying that essentially the Jacobian on each domain is close to be constant in some sense. Okay, so it depends on this way. So it's bounded distortion property. With these properties this map is so in our setting, so these induced maps, they can be used for many purposes. One of them is for deducing the existence of SRB measures. And in this setting, by an SRB measure, I mean a measure which is ergodic, an invariant measure which is ergodic and absolutely continuous with respect to the volume measure M. Of course, the notion of SRB measure is more general. Our main result as a version in the more general setting, but here I will be considering a simple situation. We don't have much time, so and I will describe the main ingredients for this result. So I think it's better to do it this way. So, and the first result, which is a kind of folklore result, is that if we have an induced map, then the induced map has a unique SRB measure, so a unique measure which is absolutely continuous with respect to the volume measure. And actually, it has more properties, but I'm not interested in the properties of the measure of the induced map. I'm more interested in the properties of the measure that it gives rise for the initial system. So, and actually, if the return time is integrable with respect to the volume measure, then the initial system has an SRB measure, which is actually unique, and unique with the property that gives positive weight to the region we are inducing. Of course, if there are the region we are inducing does not interact with other regions, there may be other regions with more SRB measures. So the uniqueness is in this sense. So it's the unique that intersects that region. And we have a formula for this. Well, here is not so important, because I'm not going to present you all the calculations, but for our work is important, this formula, because we use it for some calculations, some lemmas that I'm going to present here without proof. So we have a formula for it. This is a kind of standard formula. In particular, this sum here is the integral of R with respect to mu zero. So this sum is finite, because we are assuming that this function the R belongs to L1. So this is a standard result in modern ergodic theory. And if you want to see a proof of this, sometimes these standard result, folklore results, proofs are hard to find. And that was a motivation for my book, was writing some of the proofs that we cannot easily find in the literature. So if you want to see the proof of this, it's in this theorem and corollary. And we say, so more terminology, we say that the measure mu, which is the measure for the original system, that's the system we are interested in, we say that this measure is given by the induced map, FR. So it's given by this inducing scheme. So this is what I mean. So it's the unique measure that is SRB measure, which intersects the region we are inducing. Okay, so this is somewhat classical result on the existence of SRB measures. And so let's go to the main theorem that motivates this talk. So, which is the entropy formula. So consider now we have an initial system, F, which is piecewise C1 plus holder. And mu is a measure given by an SRB measure given by a Gibbs Markov-induced map. And if this holds, well, many of you must know many systems with this SRB measures given in this way. And we can prove the entropy formula, provided the entropy of the system with respect to that measure is finite. So if the entropy is finite, then we have the entropy formula. And see that we are in a context, you may ask, is this related to Bézier formula? Yes, because we are in a context where all the Aponov exponents of this measure is positive because of the expansion property. And so the determinant is the logarithm of the determinant, the integral of it is actually the integral of all the positive Lyapunov exponents. So this is the same form, essentially. And we have another, well, in my opinion, is a good thing, is that we characterize, in terms of this induced map, we can characterize the assumption that we need, the hypothesis. We can characterize the finiteness of the entropy of the system, merely in terms of the return time and the induced map. Okay, so this is the entropy of the system with respect to the SRB measure given by induced map is finite if and only if this integral is finite. Okay. So two remarks. One of them is related to something I just said in the previous transparency, is that we have results. Sorry, this first remark is related to a system that I'll present at the end of this talk, with necessarily by the first item with the infinite entropy, such that we don't have the entropy formula, for which the entropy formula does not hold. Okay, if the entropy, so I will refer to the entropy formula as this formula here. So the entropy is equal to the integral of the logarithm of Jacobian. So we'll actually have the reverse of Ruel inequality. So we will have that so the Ruel inequality says that the entropy is less than or equal to this integral. So we'll actually prove that the entropy is bigger than this. So the entropy is infinite and that integral is finite. So I will present an example at the end of this talk. And the other one, this is the one that is related to a previous comment of mine, is that we have similar conclusions for systems with contracting directions. For that, we use more complex structures, not the Gibbs Markov maps, but the Young-induced structures, which are actually very well known, but for those who don't know, so they had some more structure because of the contracting directions. But we also have a version of our results. Of course, here we take the Jacobian restricted to the unstable direction. And that's the result we have. And we also here, we take the Jacobian restricted to the unstable direction in both cases. So that's essentially the results. The problem is the Young structures, which are more complex. Okay, so before going to examples and proofs, I will just give you a simple corollary. So assuming we are in a situation where the Jacobian is bounded, which can happen, for instance, it's just discontinuity points, but derivative exists almost everywhere and is bounded. I'll present you an example like that. So if this happens, then it's easy to see, this is essentially chain rule, to see that we have this inequality. And so we have this simple consequence of the main theorem, which is, so in this situation, so it's the same situation of the theorem, we're just adding this assumption that the Jacobian is bounded. And then in this situation, we can put as an assumption that the integral of the square of the return time, if it's finite, then we have the entropy formula. Because if this integral is finite, you see that we, in the formula of the main theorem, we had AR multiplied by the expression here. So that's why we have the R squared. And so with this, we have the entropy finite. And with the entropy finite, by the first item, we have this form, okay? So this is a simple corollary, but interesting, and we can apply it to some examples. So let me see briefly three applications. The first one is Lorentz maps. Well, to the best of my knowledge, I didn't see in the literature any results that could be applied to these three types of maps that I'm going to present to deduce the entropy formula. I've seen people using the entropy formula for these maps, but I didn't see any result that could be directly applied to these maps. Okay, there must be ways of proving this, of course, and not using my technology, but I'm just illustrating applications. So these are the Lorentz maps. So it's not so important the expressions. Look at the pictures. These are very well-known pictures. In 2006, Stefano and two students of his, they proved that they have these kind of maps. They have induced Gibbs-Markov maps with integrable recurrence times. So we just need to add the finiteness of the entropy to deduce that we have the entropy formula. And the finiteness of the entropy is not so difficult to prove because we have mode zero partition made by the two smoothness domains. We can see that it's a generating partition because derivative is strictly bigger than 1. And clearly the entropy of the partition is finite. Since it's generating, it's easy to deduce that the entropy is finite. And so we have the entropy formula for this. The other example is derived from that previous example is Rovella maps. The derivative is no longer infinity. The derivative is 0 on both sides of the discontinuity point. Myself and Mohammed Sufi, we proved the existence of inducing schemes for these maps and with integrable recurrence times. And so we have the SRB measures. In this case, the derivative is bounded. The inducing schemes have an exponential tail, so the R square is clearly integrable, and so we have the entropy form. And the third one is based on an example by Cristadoro, Haydn, Marie, and Vaienti. They presented this family of maps, which actually generalizes an example that myself and Vitor Araújo presented in the paper of 2004 for hyperbolic times. Well, was some motivation for that. And this family, well, is defined implicitly. It's not very easy to see what are the expressions, but it's like this. So derivative 1 at this extreme points. Well, this is the circle, so it's the same point. And derivative infinity at this point. And it's made in a way that the inverse of the derivatives at the pre-image is the sum of the inverses is 1. So it preserves Lebesgue measure. And they prove that Cristadoro, Haydn, Marie, and Vaienti, they prove that they have integrable, induced Gibbs-Markov maps with integrable recurrence time. And so we can apply again. Well, again, we have to check the finiteness of the entropy, and is similar to the Lorentz maps. So we can prove that it's finite. And so again, we have the entropy formula for this. So these are the applications. They're all in dimension 1 here. There are more applications, high dimension, but the systems are not so easy to describe. So these are the applications I'm going to give here. So let's give you some idea of the proofs. So the proof uses towers. So towers are an object that is also used in a lot of situations for proving decay of correlations, for instance, large deviation, many things. So let me briefly describe the tower. So we are in the situation of the theorem. So we have the induced map, we have the partition, and we define this the tower. So the tower, assume that here I'm making this picture in dimension 1. So here in the base we have the domains and the recurrence times, and so we put more levels until the recurrence time being reached. And then we start with the levels. And so that's the way we define the tower. So the tower, first we define the domain of the tower and then the tower map, which is simply going up. So here we change the vertical coordinate, we add 1 unit. And when we reach the top, or actually 1 unit before, then we come down by the induced map. So this is the usual tower. For those who don't know, it is this. And we have the levels of the tower. The Alves level corresponding to the L here till R, and each level is a copy of a subset of the base, delta 0. And so we can extend the measure to the whole tower. And actually, we have the finiteness of the with respect to the measure, which is m here is the volume here, and in the tower you can think of the levels as also being copies of some subspace of the base. So we can also talk about the volume of the tower is equivalent to the integrability of the recurrence time. It also has a Jacobian, the tower map, which is not difficult to see if you look at these expressions, which is 1 when you go up, and when you come down is the Jacobian of the induced map, because you use the induced map, okay? And we have this result, the tower map. So assume it's associated. We can actually define tower maps more generally, but this is the situation we are going to consider here. So assume it's associated with the Gibbs-Markov induced map with the integrable recurrence times. And so the induced map has a unique SRB measure, absolute measure which is ergodic and absolutely continuous with respect to M. I called it mu0. So see that we can think of F as being a recurrence time both for the initial systems and for the tower. And the expression, so we have a measure for the tower. So we have a unique invariant measure, which is absolutely continuous with respect to the reference measure in the tower. And the expression is essentially the same we used for when we passed from the induced system to the original one. So we can think of the tower now as the original one. And moreover, and this is the property, this form is not so important at this, for this presentation, but this I will use. I will use that the measure is ergodic and the density is bounded from above and below by constants. So this is property that will be useful for us. So this is something I said before. So it's essentially using the same ideas that we didn't use, but for the previous theorem. So it's just using it. So it's, again, a result which is proved in my book. So the tower has this very good feature that is very important, for instance, for proving the decay of correlations, is that the tower can be seen as an extension of the original system. And the extension, to see it's an extension, well, an extension means that these two properties hold. That's the meaning of this. So this can think of a projection from the tower to the original space in this way, very simple. And it satisfies, not difficult to check. You can find it in the results of Young or my book if you want. So this projection is a semi-conjugacy between the original system and the tower. And it also is a semi-conjugacy also in terms of measure. So the good measure, which is the SRB measure for the original system, is the projection is a push forward with respect to this projection map of the good measure in the tower, okay? And but we need, so this is good, this is very important for many purposes and also for the entropy formula. So I'm gonna tell you now the strategy to prove the entropy formula. First of all, I use a result by Bouzy. It shows more generally if we have an extension with countably many fibers, then the entropies are the same. Okay, so this is a classical result by Bouzy, and we can apply it to deduce the entropy of the original system is equal to the entropy of the tower. And it's a straightforward calculation to show that the integral of the logarithm of the Jacobian of the tower coincides with the integral of the logarithm of the Jacobian of the original system. This is simply calculation. No ideas are involved, essentially doing calculations and checking it works. So the first item, if instead of this and here I can put an equality, we have the entropy formula. We have the entropy equal to this. Okay, so this is our goal, to see that the entropy formula holds for the tower. Okay, so that's the goal, and that's our next goal. To prove the first item, but we also derive some things that will be, and then we immediately also deduce the second item. So to prove so our goal now is to prove the entropy formula for the tower. So for that, we recall that we have a partition in delta 0, which is the base of the tower, and the higher levels are copies of the base, of subsets of the base, actually unions of elements in the partition, and so we can pass we have a partition in the whole tower. So you pass the elements that are in higher levels, and we have partitions on each level. So I'll collect them all and call it Q. So P is for the partition, the base, Q is for the partition, the whole tower. And we also consider the refinements of the partitions. by the dynamics, which is the tower. And we also consider, so this is the notation, Qn of XL is the atom that contains the point XL. And I will consider these are moments, so are positive integer numbers, which are moments for which the nth image of the atom by the tower is bigger. Actually, bigger than some constant would be enough, but we can actually, in this case, say it's bigger than the base of the tower because we choose these moments as the moment it returns to the base. And we can prove that this for almost every point in the tower, we have that this MXL has infinitely many moments, elements. Okay, so this is one of the properties. It's not difficult to prove this. And the other one is kind of standard estimate that we need for these things is the what usually people call volume lemma. Volume lemma means that the measure of nth atom, so the refinement of the partition containing a certain point, is of the order of the inverse of the Jacobian. Okay, so this is standard. Usually in hyperbolic dynamics, this holds. Here we have to choose properly the moments, and the moments are these. The moments essentially when we return to the base of the tower. So this is the volume lemma. So we want to prove the entropy formula for the tower. The entropy of the tower map is given. So what I'm saying essentially is that the partition Q is generating. Well, there are many results about generating partitions and so on, but here we are not in metric space. I didn't introduce any metric in the tower, so we can use. Well, it's not difficult to see that the infinite refinements of the partitions are made is the partition to single points, and also we have that the partitions are increasing, and so we can use directly a result by Parry and deduce that the entropy is the lemma of the entropies with respect to these partitions. But since they are refinements, it's a general fact that the entropies coincide, and so we have the lemma. This is the idea of the proof of the lemma. Just one more ingredient is what I call generalized Birkhoff theorem. So we know Birkhoff theorem, well, the standard version is for integrable observables. Here I'm going to use Birkhoff theorem for an observable, which is the log of the Jacobian of the tower, which is not necessarily integrable. But the negative part, and that's why we have this minus here, the negative part is not difficult to see because the map is essentially expanding in the tower or something which is going up, which is a translation. So we can prove that the logarithm of the Jacobian, the negative part of it is integrable. And so with that, we can deduce Birkhoff theorem. So we can apply Birkhoff theorem if the negative part or the positive part is integrable. Meaning if the integral is defined. So that's the result here. If the integral is, we can state it generally, if the integral is defined, meaning positive part or negative part is integrable, then Birkhoff theorem still holds. And so with this, we can prove not by now the entropy formula for the tower. Well, we can prove, but with an additional assumption that then we'll translate this to the original system and gives us the first item of the main theorem. So now that's when we obtain the entropy formula for the tower. With these ingredients, you don't need to read them all. I will start to use them. So I want to prove the entropy is equal to the integral of logarithm of Jacobian. We know since this is a generated partition, is lemma 5, then we have this. And then by Shannon, Macmillan, Bryman, since it's a generated partition, and here we need the entropy of the partition be infinite, we have this. This is direct application of Shannon, Macmillan, Bryman theorem. And then I told you that I was going to use that the density of the measure is bounded from above and below. So this means since it's bounded from above and below, we can essentially replace the measure, the invariant measure by the reference measure. And then, well, since these sets, they have infinitely many elements for almost all points, we choose a typical point, generic point for the measure, and we can take the moments here because this limit exists, so we can take special moments, and it coincides, of course. And then I use the volume lemma, that's the E property. I use the volume lemma, which says that they are essentially of the same order. And then with the volume lemma, I use now, well, here I use the chain rule for the Jacobian. And then, so this is the chain rule for the Jacobian. And then I use the generalized Burkett theorem. So I have this, okay? So I've proved this. This is what we need to prove to deduce the entropy formula for the original system. That was the goal, okay? But now I have to check what is this assumption in terms of the original system. So as I said, by Buzy we have this. So the original system, the entropy coincides with this. By lemma 5 we have this. And this is by definition this, okay? This is the definition of the entropy of a partition. It's a general fact that the entropy of the original partition is bounded by the entropies of the refinements. So from here, we easily deduce that entropy is finite if and only if the entropy of this partition is finite. So it is a consequence of what is said in the 2 lines above. So the first item follows from the proposition and this thing here. So recall the goal. The goal said that it was enough to prove the entropy formula for the tower. And the second item also follows from here. Because we have this lemma. I'm not going to prove it, it's some calculations, but we can prove that the entropy is finite, the entropy of the partition is finite, if and only if this integral is finite. And that's where this integral appears. So we had this expression, we didn't want to put this as an assumption, we wanted to translate, and that's the way we could translate it to the inducing scheme. You can actually prove that this entropy is of the order of this integral plus this one here. And this, by assumption, is finite, the integral of the recurrence times, okay? So order means bounded from above and below by constants, the difference. Okay, and so this is the way we prove the main theorem, okay? So we have proved the 2 items. And now let me, in this last 3 minutes, I think I have 3 minutes, right, Jacqueline?
Yes, you do.
Okay, so I'll try to give you an idea of this example. It's just 3 transparencies. So we present, I will give you an example in an interval map, so in dimension 1, with an SRB measure given by a Gibbs Markov induced map, for which we have the reverse of Ruel inequality. So see that these measures, in some sense, they are very regular, these measures that appear from inducing schemes. So there's a lot of properties that they have that we know. But even for these measures, we can have, in the case of infinite entropy, we can have the reverse of Ruel inequality. So the only possibility is having infinite entropy. For otherwise, we will have item 1 applied and given the Bézier formula. But so with infinite entropy, we can have this reverse inequality. So to build this example, I'm going to give an interval, a Gibbs Markov map on that interval, and a measurable map which is constant on each element of the partition. So with these elements, I can build a tower. And that's what I'll do. The original system will be the tower. And you may think, but the tower is not, well, you can think of the tower if instead of thinking of the levels, you put the intervals in the levels next to each other. If the sum of their lengths is finite, then you have a finite interval, and you have these continuities in the extremes of these intervals. There's a countable number of intervals, so we have a piecewise infinite map as I defined it. Okay, so with this I'll build a tower, and the tower map will have the properties I need. So that's what is said here. So you may think of the tower as a map, a piecewise infinity map of an interval, okay? And the return to the base of the tower is the original F map, because I'll build the tower out of this map here, okay? And as I said before, it can also be thought as an induced map for the tower, and so for the original system in this case. Okay, so what is so 3 things: interval, Gibbs Markov map, and the recurrence times. Well, for this, I'll use this auxiliary function, which, well, if you think of the definition of entropy, is not strange that it appears. So this function, which is C1, actually C2 out of 0, and several properties, and consider these numbers. 1 over n squared log of n. And then you consider the inverse. This is a bijection. Actually, this phi is a bijection in this interval. So you can think of phi minus 1. And we have this lemma. So this lemma satisfies these properties. So the first one is they are summable. Actually, the first one is a consequence of the second one because they are summable also multiplied by n. And the images are summable. Well, this is not difficult to see because when you take the images, you are considering this series here. And it's, well, you can use some results which give you that is summable. And when you multiply by n, it's essentially the result that says 1 over n squared log of n is summable. 1 over n log of n is not summable. So this is 3 and 4. So the only point to be checked is 2, but it's not difficult. Okay, and so these numbers by the lemma, these numbers have finite sum. So I'll call this B, and I'll consider the interval 0b, and I'll consider this partition of the interval. So I start with 2 because of this log n here. If I start with 1, I have a problem. So all these starts with 2. So the first one is until a2, and then the next ones are the a's. So you make the difference of this with this. You have in the next, for instance, for omega 3, you have the length of this interval is precisely a3. Okay, so this is a partition of this interval here. Mode 0 a mode 0 partition of this interval delta 0. So we have the interval, the partition, and what is the Gibbs Markov map? Well, it's very easy. You put it linear. On each element, you send it to the whole delta 0 and linearly. And so you have this, it's clearly expanding. And so you have this, and it's easily verified that it's a Gibbs Markov map. And what are the inducing times? Well, we can define anything we want. I'm going to put omega n equal to n, okay? The R restricted to omega n equal to n. And then I consider T the tower associated to these objects. And you can think of it, as I said before, as an interval map. Piecewise C infinity, because actually piecewise linear map in the interval. We have this, so the measure of the points which have return equal to n is equal to the measure of omega n by definition. So it's an. Well, I don't think I need this estimate because I'm not going to do the calculations. Simply mention that we have this. So the integral of R is given by this, which is finite. This is lemma 10. The integral of log of f prime is given by this, and this is finite. So it's essentially, this is finite as well. So this integral is finite. And this is not finite. So this is given by this. Well, the first part is finite, but this one is not finite. It's lemma 10 as well. So taking rho, well, rho is this integral here, which is finite by assumption. We can easily see that we have this. So you can check this. And so we have that the integral of the Jacobian of the system, so the system now is T, is finite. But by the second item of theorem A, see that we can apply because it says the entropy is finite if and only if this is finite. By the second item, we have that entropy is infinite because the assumption is that the second item is that this entropy is infinite if and only if this is infinite, or finite if and only if this is finite. So since this is infinity, we have that the entropy is infinite. And so we have the reverse of well inequality in this, which is somewhat strange because we are in a world where the measures are quite regular, but even here we can have the reverse of well inequality, of course, with the infinite entropy. Okay, thank you very much.
Thank you. Let us thank José Alves again, the first time. So.
Well, you have a lot of references.
Okay.
You have the link if you want to see some references, and you have the link for this talk.
Okay, thank you. Is there questions or comments? I don't know if there is any question on YouTube, Marisa. So far, no.
So may I ask something?
Yes, please.
Yes,
Thank you very much. So you proved the Pessin formula, yes, for this measure.
Yes. Yes.
So what do we have for Rouel inequality when you have finite entropy? But I mean for other measures, for instance, which come from lift of some measure. I mean,
Well, the problem is that see that all this is based on a partition which is a Lebesgue mod 0 partition. So if you want to consider measures in general, you have to be careful with that. So we cannot say many things in general.
Yes, I mean, if you no, not too much general, but maybe the measures, the class of measures which are lift measures. So can we define this?
Okay.
You have the measures for your induced map. You have probably Ruel inequality. I'm not sure. This is an expanding map, no? And then you consider the lift of these measures.
On the lift of the measure to the tower. So the liftable measure. Okay.
Exactly. And then maybe you can ask if the lift measures always satisfy Ruel inequality or not, if they have finite. So you prove that is not true.
Yeah, that's a nice, well, I didn't think of it. It's a nice question. Yeah. Maybe we can say something about that, of course.
Okay.
Well,
thank you.
Questions?
José, I have a question.
okay.
So what is known about Young towers for billiards in high dimension?
There are results by Chernov and Zhang. They have, well, this part cannot be applied to billiards. The other part that I said, we have a second theorem for systems with contracting directions. And for the other part, we have, but we only did it in dimension 2, but they have, I think it's Chernov and Zhang. I may be wrong, but I think it's Chernov and Zhang. They have generalizations for higher dimensions.
Okay.
At least Chernov is involved in some generalization. But
Thank you.
Yeah.
More questions? We still have a bit of time, a minute. Well, if not, so let us thank José Alves again, please. Thank you.
Thank you very much.